Up until this point, we have been exploring everything that is in closed flows, both laminar and turbulent. Laminar flows have been relatively easy to find solutions for with the conservation equations. The equation solutions completely describe the instantaneous flow behavior in space and time. We really only need theory to explain everything, and if measurements are used, they would only be used to confirm the theory. Turbulent flows have been less simple, and we find that the equations in their full form are impossible to solve. The equations can be simplified down to the Reynolds average Navier-Stokes, which we solved in the last lecture, but this only describes the average flow behavior, so what we get from this theory is very limited. Measurements are required here to further our understanding and to build upon theory. So, if measurements are necessary to understand fluids, then it makes sense that we take a break from theory for a lecture and discuss fluid measurement. Here, we will cover what we want to measure, velocity, pressure, and temperature as functions of space and time. Then we will explore measurement resolution, or how detailed we can make our measurements, and also measurement error, quantifying the inevitability that our sensors are not perfectly accurate. Lastly, we will go over common measurement devices and fluids and organize them based on capability and cost. Okay, let's have at it. First up, we cover the properties of fluids that need measurement and the ones that don't. Consider the conservation of momentum written out in its entirety. Specifically, let's examine all the variables in the equation and what we know and what we don't. The fluid viscosity, mu, and density, rho, are generally constant in Newtonian and incompressible flows. Given a certain temperature and pressure condition, both of these can be looked up. The gravitational constant is set by things like planet mass, and other body force terms also have similar lookup constants. That leaves us needing to measure the velocity field, u, v, and w, and the pressure field, p. Both the velocity field and pressure field are functions of all four dimensions: space, x, y, z, and time, t. This means that we need measurement techniques that can take data continuously in time and can access the entire flow field volume at any instant. This is nearly impossible to do. The temperature is also something that needs to be measured, though in most cases, like incompressible flow, we consider it constant and it just needs single measurement in space and time. So, we need equipment designed to measure velocity, pressure, and temperature in space and time. Before we talk about the measurement equipment though, we need to better understand what limitations it may have. Understanding the limitations helps us decide what we need. First, let's talk about measurement resolution. Again, we know that the velocity and pressure fields are continuous functions of space and time. This means that a perfect measurement could resolve space down to the molecule, where the continuum assumption breaks down, and infinitely resolve it in time. However, in reality, measurements are very limited. A camera taking a picture nicely models the categories of these limitations. Here, consider a digital camera taking a picture of our friend Osborne Reynolds. But if we were to inspect the photo with a magnifying glass, we would see the pixels that make up the photo. Every digital photo has a fixed number of pixels, usually quoted in the camera specs, and each pixel has an RGB content defining the color. These pixels have one piece of information and have a finite width and height, delta x and delta y. These are like the single data points from our measurement devices, and this represents the measurement's spatial resolution. We can only see so finely in the x and y direction, and there's no z information. Any given pixel could have color from any given z position, which is why Osborne in the foreground and the tree and clouds in the background show up on the same 2D image. Furthermore, when a camera takes an image, it leaves its shutter open for a finite length of time to collect the light. This means that technically an image is an average of the exposure time. If things are moving too fast, we would see them as a blur because the shutter was open too long to capture that motion. A camera also can only take sequential photos so fast, limiting how often we can get this average time formation, or how fast we can get a series of pictures. These two things represent how measurements can be limited in time resolution in addition to the spatial resolution. No measurement can perfectly measure large fields of view with infinite time and space resolution, and even if they could, it would require way too much data storage to be useful. Let's explore how this would look in a fluid-specific situation. Consider our laminar channel flow and the resulting flow field. In this flow field, we've placed a flow sensor that can traverse in the y direction. On the right, let's plot the velocity against the vertical location, also known as the velocity profile. First, we know the real profile is a parabola, the solution of the conservation equations we came to in previous lectures. Data points from this sensor fall on top of the real profile, however the points have a fixed spacing at a certain distance apart. This spacing is the probe displacement resolution, representing how far apart your measurements are. In practice, this can be because your traverse only can take finite step sizes, or you have multiple probes that can only be so close together. On top of this, the points are represented here having a height to them. This represents the probe size. The probe doing the measurement has a finite area where the sensing happens, which means it is taking an average of the velocities over that entire area. This represents the minimum possible resolution we can acquire data. Probes just can't resolve lengths below their sensor size, much like a camera image are limited by their pixels. Let's consider a different example to better grasp time resolution limitations. Here, we have flow behind a tractor trailer on a highway. Anyone who has ever driven behind one of these knows the flow is very unsteady. Now, let's place a fictional flow velocity sensor in the wake that takes velocity measurements over a range of time. If we plot the real velocity versus time, we see that the flow is periodically unsteady and cycles up and down in u. On top of this, let's plot our data points taken by our sensor. First, we notice that the data points are spaced apart at fixed time intervals. This is called the sampling frequency, and every sensor has a limit in how fast it can sample. This is analogous to a camera's limit in how rapidly it can take its photos in a series. Second, we gave the data points a fixed width to represent that the sensor is not taking data at a perfect instant. It takes in information over a fixed amount of time and averages it. This is like the camera's exposure time, how long the shutter is open and taking in light. This could be inherent in the sensor circuitry to ensure clean quality data, or the physical mechanisms of the device just can't react fast enough. In practice, this means that a sensor limits you in the highest frequencies that you can measure. If a super small vortex passes by your sensor very quickly, and the sensor is either too big to see the vortex in space, or the vortex causes a velocity fluctuation that happens too fast for the sensor to react, you don't accurately see that vortex in your measurement. So, when buying equipment, you want to be aware of the following things. How big your device is? This limits your ability to resolve the data in space. How finely spaced your devices can be? This also limits your spatial resolution. Also, how precise your device timing is and how fast it can take data. These limit the temporal resolution of your sensor. Now that we have a better handle on resolution, let's consider measurement error. On top of all these space and time resolution issues, there is still error associated with your device. Even if you have a perfect spatial and temporal sensor resolution appropriate for what you need and what the flow has, you still are going to measure the data at least a little bit wrong. This is due to two types of error, bias error and random error. Bias error is an error that is constantly shifted or always leaning in a certain direction. It's more predictable and easier to account for. This type of error can come from multiple sources, but most commonly is due to miscalibration, meaning the sensor constantly thinks one velocity is slightly different. Another common source for this is voltage drift in your sensor. The circuitry in the device might be slowly changing behavior due to the temperature or humidity changes in your room, or it could just be wear and tear of your circuit. Most importantly, you cannot average bias error out. Even if you average data over an infinite amount of time, you would still see this bias. The best way to get rid of bias error is to check your device against known conditions, say a velocity field that you know very precisely, and make sure the reading is correct. You can fine-tune this through a calibration yourself and correct for this error. The second major type of error is random error. This is most commonly referred to as measurement noise and is randomly distributed about the real value with a Gaussian distribution. This is mostly due to just device limitation and electronic noise that might exist in the surroundings. All sensors have noise and limitations, and the less noisy they are, the more precise and expensive they get. The noise is helped by averaging. If you were to take a longer and longer time averages, you would converge to the real value at that point. In practice, this noise is how you determine how long you should be taking data and averaging it. Now that we're aware of this noise, let's glance at how one might quantify this error. Please note this is not a complete lecture on error analysis, which usually gets its own course, but more so it's just a cursory overview of how you might encounter error in practice. A velocity measurement is equal to the sum of the real velocity at that point and the error. In reality, we want to minimize this error relative to the real value. If the error is 0.01% of the real value, that's great. If it's 10%, that's not so great. Additionally, you want to consider the final calculations you will be doing when considering the error magnitude. For example, if all you want to measure is u, then u mean equals u real plus u error, and your confidence is the measured value plus or minus the error value. That's the range that you are sure the real velocity should fall in. However, if you want to eventually calculate u squared, things get trickier. Squaring u real plus u error gives three terms: u real squared, 2 times the product of u real and u error, and u error squared. Generally, u error is small, so the squared of it is very small and is neglected. However, the term that is the product of u real and u error is bigger in comparison, and this sets your new confidence interval. In practice, when you buy a device, they've already attempted to quantify the error and present it as an accuracy either an absolute value, like plus minus 2 meters per second, or a percent of the full scale value. You can also attempt to quantify and calibrate your own error by using your device in known flows and assessing the shift and noise associated with it. This is a good way to check the device's factory calibration. Alright, we know a little bit about what we need to measure, measurement resolution, and error. So let's talk measurement devices that you will come across in fluid mechanics. These are devices designed specifically to measure velocity, pressure, and temperature in space and time. Note, this is not an all-inclusive list. I am just covering the ones that are most common in research and industry. First up, we have devices that measure velocity. The most basic is a fan-based anemometer. Generally, these are handheld and often used by HVAC engineers to measure the velocity in air ducts. As air blows through the device, it spins a fan like a wind turbine. The fan's rotation rate is a direct function of the flow velocity through calibration. The next measurement device is the pitot tube, which has been used by researchers and aircraft engineers for decades. You have a specifically designed tube that is placed in the flow field. There are 2 pressure taps, one at the tip of the probe and one at the sidewall. At the tip of the probe, the flow velocity has stagnated, so the pressure at that location is the total pressure with no velocity. On the sidewall, the velocity is uninhibited, so you are measuring the static pressure at the wall in a velocity field. Using the Bernoulli equation, you can map the difference in these 2 pressures directly to the flow velocity. Next up, we have the constant temperature hot wire anemometer, sometimes called a CTA. Here you have a small probe with 2 metal prongs connected by a very, very tiny wire. As you send a voltage across the prongs, the wire heats up, like a light bulb filament heats up. As air blows over the wire, it gets cooled due to convection. A closed-loop control circuit actively works to keep this temperature constant by adjusting how much voltage it sends in. If the velocity gets higher and starts to cool the wire more, it has to send in a higher voltage to result. Through calibration, you can directly map the voltage into the prongs to the flow velocity. Up to this point, all of the sensors we've considered have been point sensors, meaning they take measurements only at a single position in space over a length of time. Particle image velocimetry, however, can take data instantly over an entire plane or volume in space. Here, you use smoke or particles to seed a flow that you're interested in. A laser lights up the particles in the domain you care about so that the camera can see these particles. The camera takes 2 quick pictures separated by a carefully tuned amount of time. From this, software can assess the correlation between the 2 images and get the distance the particles traveled over that known amount of time. This is how you recreate an entire instantaneous flow field. These are quite popular in research, but have limited use in industry. Let's draw a map of where these devices land in terms of spatial and time accuracy. In the bottom left corner we have the fan-based anemometer. It cannot react fast in time and has a very large measurement area. These are cheap, usually under $100. Next, the pitot tube can have a much finer spatial resolution. However, pressure transducers are still limited in time resolution, so it cannot get you data at a particular instant. These are slightly more expensive and can run you a few $100s at most. Next, you'll find the hot wire, which can be very highly resolved and accurate in space and time. The wire can get down to mere microns in size, so it can measure very small and very fast flow structures. These are typically thousands to tens of thousands of dollars. Lastly, we have PIV. These can take data quite fast with super high-speed cameras, but the pixel resolution limitation and the finite size of the particles in the flow will always limit the spatial resolution of the device. However, these are easily the most expensive devices at hundreds of thousands of dollars. You really have to pay to get that full velocity field at a single instant. Next, we have the pressure measurements. These are separated into the absolute pressure, referenced against a vacuum, the gauge pressure, referenced against atmospheric pressure, and the differential pressure that compares 2 pressure points of interest. The simplest way to measure pressure difference is through a manometer. Here, a liquid-filled tube is connected to 2 points in your flow field. If there is a pressure difference between the 2 ends, the liquid in the tube shifts towards the low pressure end. From the height difference between the 2 ends, you can calculate the pressure difference. Remember, inches or centimeters of water column is a pressure unit that can convert to pascals. Next, we have a pressure transducer. These come in all shapes, sizes, and complexities. They are designed to output an electrical signal that corresponds to the pressure at a single or multiple points. Generally, you have 2 cavities that are separated by some sort of diaphragm. As a pressure difference is applied, it deflects the diaphragm. The amplitude of this deflection can be transformed to the pressure difference through calibration. If you're interested in the pressure field at a surface, which is typical for aerodynamics, you can use pressure-sensitive paint. This special paint fluoresces under a certain light source, and the fluorescent characteristics are a function of the pressure at that location. This results in a gorgeous output of color that corresponds directly to the pressure at the surface. However, it can be messy and difficult to work with. Lastly, you can also just directly calculate the pressure from the velocity field. Say you have a PIV system that we described above, and you get your velocity field. You can use Navier-Stokes to arrive at the pressure field through derivation of the velocity field, integration to get pressure, and boundary conditions. This can be incredibly noisy due to the fact that you have to do derivatives on a velocity field with relatively poor spatial resolution. These derivatives amplify the noise. Okay, let's map our pressure devices comparing spatial and time accuracy. The manometer can actually be surprisingly accurate, although it is really only good for time average measurement. The water column has mass, and that can only respond to changes in pressure so quickly. These are generally very cheap and easy to DIY. Pressure paint can have very high response rate and can be very accurate with proper calibration. However, the paint itself can be very expensive and requires a specific flow problem that it can work with. The direct calculation would need some method of obtaining the velocity field instantaneously and accurately, which is the super expensive PIV system. Pressure transducers can be very fast, but have limited spatial resolution, especially the ones that respond with high time accuracy. Usually it's a trade-off between these two. They are a bit more expensive, but they are an industry standard, so cheap versions are available. Currently, there is no method to directly measure a whole pressure field, which is a major limitation in today's research. Lastly, let's talk about two devices that can measure temperature at a point. First, you have a thermocouple, which are incredibly common in industry. Here, you have a probe with two metal wires of specifically different material that come to a point at a welded junction. These two materials generate a current flow between them, generally very tiny. This current flow is a function of the ambient temperature, so measuring the voltage potential across the two wires can give you the temperature with proper calibration. Next, we have the cold wire anemometer, or CCA. This is the same idea as the hot wire that measures velocity, but here the wire is not heated. As the temperature changes, so does the wire resistance because a material's electrical resistance is a function of its temperature. You measure the resistance of the wire via the voltage drop across it, and you can map that back to temperature with the calibration. If we put these on our chart of spatial and temporal accuracy, the thermocouple is usually in the bottom left. There is a limit to how small they can be made, and they do not change very fast in time due to the mass of the welded junction. However, they're dirt cheap. Cold wires are more expensive and require similar resources as a hot wire, so tens of thousands of dollars. These can change temperature very fast and can be made very small. To summarize, when you choose a measurement device, you want to consider your own needs in terms of accuracy and resolution in space and time. This requires having some speculation about the type of flow field you are measuring. Is it laminar and clean with large, coherent structure? Or is it a chaotic, turbulent mess with microscopic velocity fluctuations? Also, you'll certainly have some sort of budget. A PIV system is nice, but not many companies have that kind of capital for a single piece of measurement equipment. Okay, let's review. First, we justified why measurements are needed in fluid mechanics. By looking at our equations, we decided what needs to be measured and what properties can be looked up in a book or online. We covered spatial and temporal measurement resolution and how that looks as we plot it. Two types of error were discussed, bias error and random error. Both can be controlled with specific strategies. And last, we covered the common velocity, pressure, and temperature measurement devices and compared their spatial and temporal accuracy as well as cost. Next time, you'll be introduced to Project 1, where we'll do some measurements of our own and use these concepts. Thanks for watching.